Hello, good morning, good afternoon, and good evening. Welcome to this World Large River and Delta System Source to Think webinar series. Today, we invite Professor Uri Schattner from University of Haifa, Israel, to give a talk about the Nile River derived sediment across the Eastern Mediterranean Sea. So before I introduce Uri, and I would like again introduce our next webinar next week, next Wednesday, September 16. We will invite Professor Robert Nichols from UK, University of East Anglia. He will talk about the delta, the human impact, how the delta evolution. So please mark your calendar next Wednesday. And the same time, we're coming back. So Uri is from, again, from University of Haifa, Israel. He get his master and a bachelor degree from Hebrew University in Jerusalem, and both master and PhD in Tel Aviv University. And then as a postdoc in Israel, and also postdoc experience in University of Leeds, UK. And one thing I would like to say, Haifa is a beautiful, beautiful city. I guess maybe many of you never visit there. If you have a chance in your life, please visit there. It's very nice. And the university, the campus is sitting on the top of the mountain, on the peak of the mountain. And once I did walking all the way from campus to the Bahai Garden, as you can see from the picture, is beautiful. So Uri, I try to promote the tourists of your city. So now I will give to Uri, and he will talk about the Nile River derived sediment, because Nile is the longest river in the world, and the fate of the sediment not so many people know. So I think that's very important to talk. So Uri, I'll give to you. So go ahead, you can share your screen.
I will share it. Just a second. Can you see my screen?
Yes.
Okay. Hello, everyone. And thank you for taking the time to watch this presentation. And a big thank you to Paul for making this happening. I mean, this is a great initiative, and we are all grateful for being able to see this international conference, actually. So today, I would like to speak with you about a source to sink hierarchy. What does it mean? So we all know about source to sink. It's a great way to understand sediment transport from the source through the transport to the sink on land and offshore. And then we all are investigating what's happening in the offshore, how the sediments are accumulating, and how what the accumulation patterns can tell us about the source itself. So we study also the provenance to see where the sediments actually come from. But where do the sediments really come from? Because if we watch the sediment come from the fluvial systems to the ocean, and then they are deposited, if we think the other way around, from the ocean to the source, it's a little bit tricky, because yes, we know that most of the sediments, or all of them, are coming from the fluvial systems, but what's happening offshore? We saw this great example in the presentation from Paul, showing us the great rivers of the Ganges, Brahmaputra, Yellow River, all of them discharging so many sediments to the ocean, and then the source to the sink, and we have a sink filled with sediments gradually. But when we look into the details, the picture is a little bit tricky, because for example, here in the Yangtze River, we see that the river is taking the sediments to the offshore, and then what's happening? What happens? It goes sideways along the coast, and just imagine if we take some course from this site over here, will the sediment be from the Yangtze River or maybe from the nearby land? How can we tell? So we try to find the provenance. If we go to the details that we saw in the presentation of Paul and in his papers, we see that about 30% of the sediments that come to the offshore, they travel about 800 kilometers over here. So these are sediments of modern times or almost modern times. But what happens if we want to study a river that was going from land to the offshore 10 million years ago or 20 million years ago, and we take some course over here? So where did the sediment come from? In the source to sink pattern or approach, we think about linear, maybe a little bit more sophisticated, but what's the role of this long shore transport? So again, from Paul's presentation, the very important conclusion that not much river-derived sediments are transported across the shelf into the deep basin or deep sea. Instead, a large portion travel along long shore transport. And this is very important. We see all the rivers here from the papers of Paul. All of them are contributing so many sediments for the long shore transport. So many sediments for long distances, 800 kilometers, 600 kilometers. So this is the starting point for my presentation. And one thing, there are many things in common between these rivers, but one particular thing is they all discharge to the ocean or to a marginal sea, which means that there are many components over here of currents and deep water. And that's why we focused on the Nile system. And in the Nile system, actually, the picture is much simpler.
Hey, Uri, sorry.
Yes.
If possible, could you move the microphone even a little bit close? Because
like this is better?
Yes.
Okay. So in the Nile system, we have one source, which is the Nile, one sink, and this is a confined basin, which means that the sediments arriving into the Mediterranean, they don't live. There's no ocean taking them anywhere. And if you look closely, you see a desert over here. You all know about these deserts. So no sediments or hardly any sediments are coming from these deserts into the Mediterranean. This is the only river. So with this simple system, let's try to understand what's happening in the Mediterranean itself. We have the Gibraltar and the Sicily Straits. And in the Mediterranean, there are four main water bodies. The upper one is the Levantine surface water. Below that, we have the Atlantic water going into the Mediterranean, the Levantine intermediate water going out. And these are very important three water bodies. And below, we have the Eastern Mediterranean deep water. All of those will play an important role in our story. So we have one source, we have one sink, we have the circulation over here, and we have a desert. But actually, the Sahara was not a desert before 3 million years ago. Now it looks like this. But before that, before 3 million years ago, more or less, there were several fluvial systems throwing sediments into the Mediterranean. And we know only about part of them, and there's a lot to study in the Sahara. But there was more than one river, and this is the important thing. Also, the topography along this side was milder, less accentuated. So sediments arrived into the basin, the Mediterranean. Let's look at this part over here. And we call this part the Levant basin and Levant margin. That's the continental margin. So sediments arrived and they were carried, some of them were carried by the currents from Libya and Egypt all the way like that. But this is the present day arrangement of the currents, of the water bodies moving all over here. So they came all the way until the Levant margin, and we will focus on this part over here. These sediments, before the Sahara became a desert, they accumulated in the basin, as you can see in the multi-channel seismic reflection profile here. The Levant margin, this is the profile, and a thick succession of Pliocene sediments. When the Sahara became a desert, the basin itself became starved. Hardly any sediment arrived into the basin. We will look into this transition and what happened in the basin. But look what happens on the margin. A huge succession of Pleistocene sediments. So the basin itself over here and the margin over there. So the transition from Pliocene to Pleistocene. We have a desert in the Sahara. We have the Nile discharging, and the rivers that used to flow from the east here and there are many studies about that. They were blocked by a mountain range that became more and more prominent and by the transformed valley. So this makes the work. And the contribution of this side is negligible, as also was shown in several studies. Most of the sediments that we see in this area, the Levant basin and margin, they come from erosion of the fan and from the discharge of the river. That's the source. This, we made an overview of what's happening with the Nile system, and you can read all about it in this paper over there. And so the sediments are coming into the Mediterranean. The currents, the longshore currents, are taking them along the margin, and for many years the final sink was thought to be the Haifa Bay over here, just next to the university, no connection. And okay, but this is quite strange, because if we look closely into this area and we take into account that this longshore transport was explained for many years as a transport extending 30 meters down and 300 meters across into the basin, 300 meters. But then we see this enormous bathymetry, exaggerated, of course, vertically, but you see the scale over here, so many sediments, so many features. So how can you explain so many features with these longshore transport that goes along the coast, 300 meters next to the coast? It's a little bit difficult to explain it like that. So we wanted to find what actually builds the Levant margin. So we have the Nile is the source of sediments, and we have the longshore transport. But then we need to look into the morphology. What are the clues in the morphology? So let's start. We have two very big slides over here, the P and the D, Palmachim and Do. And in the southern part, we have a lot of small slides that recently were published in a great paper by Gadol. They made a semi-automatic detection of these slides. In the north, when we cross this slide D over here, there are no small slides, only submarine canyons going down the slope. We will touch each and every feature over here. But the boring part, quote unquote, is this shelf and shelf break. Here are most of the clues. We have 1, 2, 3, and 4 morphological belts. So if you look at 3, for example, these stripes are going all the way, and actually they follow bathymetric contours, also number 1 and number 2. So the structure of this talk, first we will talk, we saw a little bit about the primary source to sink system. This is the Nile with the sources and going to the coastline, and then we have the sink in the offshore. So that's the primary system. But then we have the Levant margin, and we have the secondary part with no source of sediments from on land, the nearby land, only source of sediments coming along the coast over here, and the secondary sink over here. That's why we called it the hierarchy. We will first talk about this connection between the systems, then we will talk about the secondary sink, and then the deep basin. In order to do so, we analyzed the bathymetry of the margin. Red is shelf, green is slope, and blue is the basin over here. We took many single channel seismic reflection profiles and also analyzed the bottom currents velocities that were measured before. Sometimes it's easier to look at the bathymetry when you look at the slope angle. And here you can see on the shelf, that's the shelf, morphological belt number 1, 2, 3, and 4. And they follow, ignore this slide, please. They follow the shelf, and we lose, as we go north, we lose belt number 4, and number 3, and number 2, because the canyons are cutting into the shelf, but the belt number 1 continues to the north. It crosses this elevated structure, and it goes to the Haifa Bay over here. Then, this is actually the path of sediment transport. The sediments do not stop over here. They fall into the basin, and we will talk about this fall later. They fall into these canyons. So we have 4 morphological belts. Let's look at the area in the middle over here. And we can see that these morphological belts of smooth, and wavy, they follow exactly the bathymetric contours. Here we have the smooth one, and the wavy is actually built from the sediment waves, which are elongated. They're not crescentic, they don't look like dunes, they are elongated because they are arranged by currents. That's the shelf break. Let's take a look at this cross-section over here. This is the cross-section, and what we can see here is the belt number 1, we have truncation over here, and the position of the shelf edge cliniform, which is actually a contourite cliniform. Sediments that are eroded from the upper part are falling into the lower part and forming the sediment waves. These sediment waves are elongated. They start growing from this erosional surface, which is the LGM erosional surface, and they climb upwards, not vertically, they climb up slope. And then when we go further, we have the belt number 3 with the smooth, and the wavy belt number 4. Now, if we look closer into this, and we did, this pattern, if it represents the flow of currents, 1, 2, 3, and 4 morphological belts, we can see this pattern at least 4 times in the subsurface until the multiple. So we see at least 4 regressive unconformities of sea level change with the wavy pattern and the smooth pattern all the way down. So possibly the currents that formed this acted at least 180,000 years in the past until today. We checked the sequence stratigraphy even further down, and we have about 13 sequences, but the resolution of the multi-channel data is not enough to see the wavy and the smooth patterns. So what we think is several currents carrying the water bodies are flowing along the continental shelf slope, the upper slope, but not in the deep basin. Sediments that fall into the basin, they are arranged as sediment waves, but elongated ones over here. So let's jump into the present. And what we did in every year, we take the students for the educational cruise, and they collect data along this transect and many other places. You have the morphological belts in colors down here. And as you can see, the water are stratified: temperature, salinity, fluorescence. And actually they're stratified to show the water bodies that we know from the previous pictures. We have the temperature and the salinity, and they're so different from each other that it's hard to miss. We have the Levantine surface water, Atlantic water, Levantine intermediate water, and Eastern Mediterranean deep water. So actually, what we see in this picture is quite a dynamic picture, because yes, it is a cross section or several cross sections, but the water are flowing northwards, that is into the screen. So, and how do we know that they flow? Because measurements that were carried out over 10 years show that during the winter and the summer, the currents flowing along the slope and the shelf edge are very strong. They are almost 30 centimeters per second, almost, and they flow to the north. So it's not all year long, but half or part of the year. And we know from the stratigraphy that this pattern of currents existed something around 180,000 years into the past. So what we suggested in this study over here, that these three upper water bodies are flowing along the coast. This is a big longshore system that we call Levant jet system, which is actually the secondary source. This is the source of sediments to the entire Levant margin. They flow along the coastline, and they don't stop in the Haifa Bay. They leave some sediments over here, but then they are injected into the basin. Later, we will talk about what's happening in the basin. So until now, we saw the primary system, and then we talked about the secondary source that brings sediments to this part of the basin. And also you can see it in the map on the right. Now we will talk about the secondary sink. So what is the pattern of sediment distribution across the secondary sink in the basin? Well, let's start with the high stand processes. And we will take a different look at the Levant margin. Now in this direction with the vertical exaggeration. Here are the big slides, 1 and 2 over here. And we have the Levant jet system flowing with sediments, making the erosion and deposition, flowing along the margin like this. And extra sediments are falling. They're falling into the basin. And when they fall into the basin, they form an unconfined sediment distribution over here. And this takes the shape of sediment waves. Again, sediment waves, but different ones. So let's take a look at this cross section over here. And remember, below 350 meters, this is the area of the Eastern Mediterranean deep water. So the cross section looks like this. Here is the location, and here we were able to see in the Pleistocene at least 7 different sequences with erosional or hiatus between them. And we have sediment waves that are climbing up the slope and therefore they are upslope migrating sediment waves forming cyclic steps. So they represent sediment distribution that comes down the slope, but actually, do we need water to flow to the east in order to form these sediment waves? So according to some models, like this one of Hoffman, sediment coming down the slope as turbidity currents, they form sediment waves, but actually the upslope progression here doesn't need any deep water seafloor currents to flow from west to the east. It means that if this is correct, we don't need any currents to flow along the margin or from the basin to the margin. And actually, this fits very well with what we saw in the oceanographic measurements with our students. So we have, during the high stand, we have unconfined distribution, as you can see here. And during low stand, we guess that we have these hiatuses between the sequences. The low stand on the shelf, as you saw, has 13 sequences and sequence boundaries. And in the basin, we saw only 7. Maybe it's something with the resolution. So we went back to this area and we published this year a paper with chirp data. We saw not enough. We saw only 7 sequences. I think we need to study this area a little bit more. But what we did here is we mapped each and every sediment wave, the length, the height, and we did statistical analysis of the sediment waves over here. You can read about it in the paper. And the cross section is over here. And when we look at this part, we have the backscatter data. So we see the intensity of a reflected signal of the multibeam, and we see these gentle funnel marks. It means that the sediments going down today or during high stand conditions, they flow down the slope into the continental rise, form these sediment waves, and also flow to the northwest like that. So this was published this year about the multibeam bathymetry. And in 2018, we published the structural implications or structure and stratigraphy of the Levant margin. 2017, we divided between the Pliocene and the Pleistocene. In 16, we talked about the stratigraphy and the gas fluid migration in the Levant basin and margin. 2016, we introduced a hierarchy of the source to sink systems. And 2015, we introduced the Levant jet system. So you can read all about it here. And so what happens in the low stand period? So let's get back to this image. During low stand, we all know that the sea level drops, so the shelf is exposed. And so the Levant jet system, if the Levant jet system was flowing there, it was flowing further away, a little bit to the west, and not on the entire shelf because it was exposed. It means that the capacity to carry sediments was much lower. And if sediments were carried over here, they fell into the basin along these routes over here. So these are confined paths or with turbidites, maybe. And let's look at them again like that. So we have the high stand deposition, high stand, and the low stand features, which are these channels that we see over here. Let's take a look at the cross section in this area. And it looks like this. The sequences 1, 2, up to 7, or up to 6 over here. And the truncation of reflectors, because here we have a truncational erosional channel. And if we go to the models, for example, this paper of Hubscha in 1997, we see that normally when we have a turbidity current going down, so we have an erosional channel, and then later on we have some deposition and the channel becomes narrow, and then we have levees forming on the sides. But here we don't have any levees, nothing. This is just erosion. So it means that there were some catastrophic events, but without any deposition, nothing. Let's continue to the deep basin, the deep basin processes. If you go and check for models of how water are flowing in the Mediterranean, you will see this picture. So you have the Black Sea, the Aegean Sea, the Adriatic Sea, and now we are interested in these Eastern Mediterranean deep water, the water body over here. And it's not that clear. Until now, you saw that it's not really flowing anywhere. And the oceanographic studies show us that these water used to come from the Aegean Sea, but now they come from the Adriatic Sea. And this transition happened about 30 years ago. And they show that there are some upwelling over here. We checked in the geology and the geophysics, and we didn't find any clue, not today and not in the past, for these upwelling over here. So here they talk about, they show the measurements, the oceanographic measurements along this transect over here, and the transition of the source of the water from the Aegean Sea to the Adriatic Sea. But the evidence show that there is no upwelling in the Levant margin along this area over here, and actually no evidence for deep water seafloor currents over the basin floor. It's a water body, but it's not flowing, maybe not fast enough to move the sediments. So let's see, let's have a closer look at this deep basin. Until now, we saw the secondary source, and it throws the sediments over here. This area is limited by, as you can see, the resolution of the bathymetry. It's about 5,000 square kilometers. And you can see here the sediment waves and the erosional channels. Sediment waves from the high stand and erosional channels from the low stand periods. And these are the erosional channels. So what's happening over here? This area is, has a lot of, it looks like sediment waves, but actually these are folds that are forming because of salt tectonics in the deeper part of the subsurface. And between these folds, we have Nile sediments accumulating, but still not covering the folds. We published this in 2016. Then 2017, Thibault et al. Published the bathymetric map, the coverage of the bathymetric map, and also the backscatter from these multi-beam bathymetry. And from the backscatter, they calculated the grain size. So we have coarse grain and fine grain over here. It looks a little bit strange to see two areas, but then when we compare our study with the new measurements, we see that it's a perfect match. It means that this coarse grain part is actually the distal deposition of the Nile. The sediments are carried by the currents and they fall down into this continental rise over here. Meanwhile, sediments are arriving in a direct route from the Nile into this area. So in 2020, we summarized the multi-beam cover, and here it is. You can download this from the internet, and there is supplementary material for whoever wants to use it. And you saw this already, but if you look at the slope percent, you see the difference between this area, the continental rise over here with the sediment waves, and the folds. But now we see another feature, which is these very nice deep water channels. These deep water channels, they flow only from south to north. They don't come from the east to the west, none of them. And we have here the folds in pink, and in the blue, we have the faults, and we're not going to talk about them. So let's take a closer look. The channels are beautiful. They all show with all the marks and the clues that we can take from them that the flow is going to the north. From here and from there, you have all the data over here. And let's take a closer look at this part, because we have in some areas overspill deposits going around the turns, like you have over here and over there, but the flow is going to this direction. So we have here 3 bundles of channels, and they're all going to the north, not only the recent ones, but also the paleo channels. It's a little bit difficult to say which channels are older than others. If we take a look at this corner, at the western part of the EEZ, you see the channels crossing faults, which are related, the faults are related to salt tectonics, and these are folds related to salt tectonics. And if you take a closer look, you can see these fans crossing the folds. Take a look at this. They cross the folds, and they cross again, and they fill the gap between them. And this is a deeper look, because this is a spectral decomposition of 3D seismic reflection data over here, which is nice. And let's look at this part over here, and you can see that some of the channels are older, some of them are cut by faults, some of them are cutting faults. So not a lot of deposition in this area, as we saw before, and we can see that the basin is starved, so the faults are preserved, and there is a long history shown over here. So if we go back to the beginning, let's say we're going to collect some cores over here. So we need to know where the sediments really came from, because until now, in most of the time, we saw in the literature that these are Nile-derived sediments. But now we know that the sediments arriving in the direct path, they go between the folds of the salt tectonics and along the channels. The channels are going all the way to this part of the trench around Eratosthenes seamount. So they're going woo, like this. And the secondary part is taking sediments from the continental shelf, along the continental shelf over here, and into this part over here. So we talked about the secondary source and the secondary sink, and now we talked about the deep basin over here. Let's try to take everything together and combine the high stand and low stand conditions. So during high stand conditions, we have the currents going along the coast or along the shelf, and taking sediments, some erosion, some deposition along the way. Sediments are falling into the basin and forming unconfined turbidites and asymmetric cyclic steps in the basin over here. And during the whole time, we have the channels flowing to the north from offshore Sinai and offshore Egypt. During low stand, we have the exposed shelf. The Levant jet system is flowing in the outer shelf. It cannot really carry a lot of sediments, and we have catastrophic collapses along confined channels, confined turbidites over here. And again, during the entire period, we have these channels. Maybe they change the shape of the channel, but they're still flowing in to the north in the basin itself. So in this area, we have one source, one sink, and the confined basin, which makes life very easy and interesting. And I hope that now we know a little bit more about the Mediterranean, but I want, this is the last slide. I want to go back to this very important slide that Paul showed us. The longshore transport is very, very important. We see from many, many rivers, but now I think it should take a very central role in provenance reconstructions, because if you find sediments over here, you need to follow all the way back to the source, which includes a long transport along the coast. So thank you for listening, and thanks for all the software that we use, and I mentioned all the colleagues with the papers, and thank you.
Oh, Uri, thank you very much for such a interesting talk. And the system you present to us is, how to say, it's very unique compared to the system we have already studied, like the Amazon, like the Mississippi River, like the Yangtze, like the Mekong, like, you know, because many large river systems, we know they do have a big portion of the longshore transport, but they don't normally in a narrow shelf. So they don't have that cross shelf portion. And yes. So the Eastern Mediterranean Sea is just like the California shelf, is very narrow, active, but California, they don't have that large river longshore drifting sediment supply. They do have a small one like the Yale River and the Columbia River. But your system is so wonderful. You have the longshore drifting, you have the slope, you have a turbid current, you have the gravity flow, you have the slumping, tectonic. That's a fantastic source to think study case. So we should talk about more. But let's back to the audience. If you have any question, you can directly ask, just unmute yourself. Or you can type your question in the chat room. So if anybody have any question, you can unmute yourself, just ask.
Okay, I don't see the chat.
Yeah, Annie.
Okay. Yeah, hi Uri, hi Paul, thank you for a very interesting talk. I do have a question about those long run-out length channels on the Nile fan, which seem super long and very sinuous. So can you comment on how long these actually are? And
these ones?
Exactly. How long are these, and how does that compare to, you know, other submarine channels? Are these abnormally long in run-out length? They seem to cross, you know, half of the Mediterranean basin, or is this still within like a normal range?
Actually, I didn't compare these channels to anything, and as you can see, the interpretation here is limited by the bathymetry data over here and over there. I think that now there is more data next to the Eratosthenes and just a little bit to the south. I don't know. I think this is a subject for many studies. There are many things to study over here. One of them is the length, and another is the sinuosity, and another is why do they not interact with each other, and where do they start, and the overspill deposits over here and over there. So I'm just guessing that to have so many channels going to the same direction and not interacting, this is special. But I don't
Even
know.
Though they are sometimes deflected by the faults that are actually oriented west-east. So you would think that there's interaction at some point, right?
So you see the folds in pink and the faults. These are strike slip faults from several generations, but these are a little bit more complicated over here, but you see that the channels are just going to the, I'm guessing they flow to the deepest part of the basin, which is just next to the Eratosthenes seamount. And if you look at this map, okay, this map over here, you have the trench around Eratosthenes, and this is the deepest part. Actually, you can see the contours. This map is from 1994, Hall 1994. And you see the contours, and the channels go to this area, and the sediments are going to this part over here. So is it long? I don't know. We should compare them to other places.
Yeah, I think that this can be done. There's a couple of studies out there that that do have long profiles. So I think these are really interesting. And usually, you know, what I'm used to is looking at a submarine fan where you usually have one active channel and it evolves, and then there's another one. But all of these sort of parallel, very sinuous channels, I've never seen that anywhere else.
Yeah, so let's do it.
That's very interesting. Okay, we have a question on the chat room. Uri, can you see the chat room? Can you click the chat? So in the chat, he said, "Thank you, the great talk." This is from Chimpeng Tan, and he asked, "What's the difference between the upslope migrating clinic steps at the basin floor and the VV belt on the shelf? They look so alike from the seismic sessions. Are they formed by similar or same process? Can you explain more?"
I think it's a good question, and this is very confusing because these are actually sediment waves, and these sediment waves, let's go back to where we see them. For example, here. Yeah, so sediment waves, maybe we'll go to the beginning. The sediment waves are formed by particles going down. I'm sorry for this, just a second. Okay. So here you have probably sediments going down the slope over here and accumulating on the upper part facing the land over here, and the crest going sideways. So this is very similar to what we see in the deep basin, in the continental rise. But the difference is when you look at the map view of these sediment waves is, let me take a closer look over here. So these are elongated sediment waves, elongated like this. What you see, the darker parts over there are comet structures and part of the LGM erosional surface that is puncturing up through the soft sediments. So that's why you see those holes. These are not pockmarks, actually. But so you see over here, the sediment waves are elongated along this trend. But this is a little bit different than what we see in the deep part. For example, in this map, they are elongated, but they are higher, much higher above the surrounding. I mean, in the shelf, it's about, let's say, 1 meter above the relative to the surrounding. Here it can be 10 meters. And they're elongated, but you see that they're not continuing all the way, because not only because the channels crossing here, but also because they cannot form larger sediment waves. They're restricted.
Okay.
I don't.
Okay. So are those waves still active now, right? Oh.
Yes, I think so, because now we have the shelf covered by water and sediment falling into the basin, and this is actually, we know that from the chirp. And as you can see, there is a new sequence. I put here interpretation, but here this is without interpretation. You see that this small bit, this is the newcomers over here. So you can see them facing the land.
So that's interesting. Okay, we have other talk from Clark Alexander. Clark, you want to ask directly? Can you unmute yourself just to ask?
Sure. I was very interested in those north trending channels in deeper water. there's obviously different stages of infill in the different channels. I was wondering whether you thought that infill occurred more during high stands, during low stands, during both stages of sea level.
So let me go to thank you for the question. The answer is we don't know. So if we take a look at this, you can see very nicely that there are several generations and several types of flows. These are the folds, and here we have traces of flow. And if you look closer over here, we can see some swings that are cut by more modern channels. But so there is a history behind what we see over here, but we cannot actually say the timing today.
Yeah, I was thinking about you had a grayscale bathymetric image where you could actually see different channel systems, not cross-cut and cut off within them, but yeah, in there.
Yes, and this is a great start for new projects, just to sample on the sides, in the middle, and just to take one or two channels over here. But one of the main reasons why we really investigated everything, so next time we go and take a core, it will not be a shot in the dark. So we will know if we're taking from these fans over here, these fans, or the channel on the side of the channel, the overspill. You see here you have some overspill, and now it's a good basis for the next work.
Wonderful, wonderful. That's a great. I think Uri, your talk definitely can stimulate many new ideas, and I think we can talk about later. But that's the one. So looks like we so far your presentation didn't show any the accumulation rate. So we don't know even, so in the near shore, on the shelf, on the slope, how fast they accumulate at the modern age, like a 100-year scale.
100, no, but we have another research, I didn't present it over here, about the Haifa Bay, because we were able to make a stratigraphy of the post-LGM and to see actual accumulation rates. And what we have, I put it after this one. So in this paper, we see the gas going up, but if you look closer over here, this is another paper that we published. That's the LGM erosional surface.
Yeah.
And so this is the LGM erosional surface from 3D seismics.
Yeah.
You see those pinnacles. And this is the thickness of the post-LGM. And from this thickness and the seismic stratigraphy, we can know the erosional, the positional rates.
That's good. You know, definitely that's a very interesting system. You know, we need to put a multiple team, even including our colleague from all the way, you know, we're working here. And so we talk about later. But thank you very much. If anybody have any question you can ask. And so once again, this presentation is recorded and available on YouTube now. If you didn't find your student attend this meeting, you should send the link to them, ask them to watch that, and for your research group discussion. But before we end, I want to once again emphasize our next week the talk. So next Wednesday, so we will have Professor Robert Nichols talk about the global delta anthropocene, about the human interaction with Holocene world large delta systems. So other very interesting talk. Please come back. So If no any other questions, so we can stop here. So thank you very, very much. And thank you, everybody. Please come back next Wednesday. And we also have another talk on Friday. Okay, thank you very much. Okay, bye-bye.
Bye-bye.
Uri, we should